My name is Dominique. My quest in life is to make complex things visible so people can make sense of it and take action. And I will not stop my quest until I found that plan again that was lost overnight when it rained, that these 4 girls discovered to save the planet. So let me introduce myself quickly. Where do I come from? What I do right now? I studied right here in Basel at the university, physics actually, not computer science. After that, I got interested in data. I moved west to IBM. They have a research lab in the Silicon Valley. I spent a few years there building up a center of competence for visualization. After 4 or 5 years, for reasons which are not obvious anymore, I moved back to Switzerland. Joined as a Swiss, once you have to work for a Swiss bank, one used to be proud of that. That changed a bit. So let's move on, but they have lots of information, they have lots of data. Essentially a bank is doing nothing else than move information around. I founded a company, Macrofocus, out of the bank, specialized in interactive visualization systems. I still work at that company on the side, but my main tasks now are at the University of Applied Sciences, Fachhochschule Nordwestschweiz, right here in Muttenz, outside of Basel, at the School of Life Sciences. So I apply these things now in the area of life science, essentially. So when I was researching a bit my projects that I've done in the past, I came across one problem, namely that, so that's a little detour here, namely that digital media rots, it decomposes. If you try to find your old things, it's not obvious that they're actually, this format is still supported. Have you ever tried to read in a Super Video 8 tape again that contains your data? Well, it's not easy. So if someone has one of these drives, please see me afterwards. CD is the same problem. Some of my backups are on CDs. This thing doesn't even have a CD reader anymore. External hard drives, USB. My new Mac doesn't have a USB anymore, so also no luck. Of course, in the cloud, should we go to the cloud? Well, clouds are notorious. They disappear without you noticing. So I'm not sure that's a good idea either. So it's an open problem. Just funnily enough, we can still read Leonardo da Vinci's drawings. You know, they survived, but my digital media is decomposing quickly. Anyway, let's get to the topic. First, I'd like to present some of my earlier work where I mostly worked on data which has a space-time component to it, physical things you can touch. So this is a pretty cool instrument. It's a scanning tunneling microscope. It's small and it can basically scan across a surface. There is a little current that's flowing with a feedback loop so that when it hits something, it retracts and tries to keep that current constant. And with this, you get a profile as you scan across the surface. And the data it produces essentially is a grid of points, grid of data values that is representing the height here. And then you can reconstruct out of that. You can reconstruct the surface and make it look, well, real. It's not really real because it's just scanning. You know, no one has seen a surface like this, but you can make it look like a surface. And the problems here in terms of visualization are not so much the visual metaphor that's given. You know, there is a bump, it's an atom that's on the surface. It's more choosing the right color scales. It's more designing it the way that it communicates what you want to communicate. Namely, in this case here, they constructed a ring with individual atoms, and you can see then the standing waves that appear of the surface electrons. They behave a bit like, it looks like water, but this is electricity that forms standing waves, and that was the purpose of this image, is to capture the imagination of people looking at it and highlighting, choosing just the right color map that highlights these features. So that's spatial metaphor, that's easy, but it's the design that's tricky. Same here. This is a simulation of a crack. We pull on both sides and we will see the crack opening. Each dot is an atom. The simulation is about 2 million atoms. And as you as the crack goes along, we follow it. As it moves up through the material, we can see it starts zigzagging, and whenever it zigs or zags, there is something going off to the side. And it turns out that these are like dislocations in the grid of the atoms, and that's interesting, but it's difficult to see here. So again, the visual metaphor is not really difficult, but it's how do you represent it, how you design. So what we tried is to visualize the displacement, not just the atoms directly, but the displacement of each of this atom as a grayscale, and then see what happens. Again, we pull on both sides, the crack goes up, and now you can see how these dislocations move through the material, how they reflect off of the sides of the material. And so now you understand what's going on, right? Okay. So next example are membranes, again, simulations of membranes. And first we need to show how do we represent these membranes. They consist of atoms and connections between them, and we represent them as smooth surfaces with the back and front side colored very differently, so that we can see as we animate the simulation what's going on, namely that depending on the interactions between the atoms, it crumples up like this, or it stays flat, like in this case, if there is not enough interaction. Right? So these are typical so-called scientific visualizations, space-time related visual metaphors. It's more about communicating things that scientists discovered and finding the right design. Now, more and more after, so that was like in the 90s or so, but more and more abstract data started to appear, and people wanted to analyze that as well. And so more and more people come to me and ask me, like, can you analyze that? It's like, yeah, let's see. So I always ask two questions when I talk to people. Is first, what data do you have? And the second question is, well, it's a meta question. What questions do you want to have answered? Because that's really the key. So now let's see, when you ask the first question, typically you get people tell you all sorts of systems. We have these wonderful, we have PACS, DICOM, hospital information systems. Everyone has SAP, unfortunately. There are warehouses. But then when you actually try to get the data, suddenly things look much different. So the real question you actually have to ask is, what data do you really have? And then it turns out it's much more difficult. You spend a lot of time actually getting it. And usually the answer is much simpler. It's just, you can be lucky if you get a bunch of CSV files. But I love CSV because you can read it and you can do stuff with it. So that's the reality. People really underestimate how difficult it is to get at the data. Particularly in the life science, I work a lot with hospitals, and there are privacy issues. The systems don't talk to each other. There are legacy systems and so on. So now the second question is, again, it's not so easy, because what people always know is that they do have a problem, but they don't usually know exactly what the problem is and what they want precisely enough so to give you instructions, essentially. So the answer you typically get is, yeah, so I know it when I see it. So you just have to start somewhere and iterate and explore. That's my experience. So once we're beyond these two questions, there is a very simple process. 3 steps is like, first get the data, clean it, that takes another big amount of time, and then explore it with your standard tools. There's Tableau, Excel, all that stuff. And one could talk now about each of these points. One could have a 20-minute talk, but I would like to focus on a 4th point tonight, which is write code. Like when all of these, we basically get here, usually like the tools don't do what you want, or there are some other problems, so you need to write code, and that's what I like to focus on tonight. So why would you write code? So there are several. I went a bit through my project, and I came up with like five reasons, or why would you write the code. And I'll give you an example of each of these. So the first one is certainly data is in a weird format usually. It doesn't, well, if you're lucky, it comes in CSV, but consider this, this data here. It's when our first daughter was born, you're very nervous, and they don't sleep at night. They're supposed to sleep, and did they sleep enough? So they advise you to keep a sleep journal. And so what you do is you take a piece of paper and you mark every time. There were no mobile phones back then, so you mark every time. So that's one day, one line is one day, and so you mark when the baby slept, and the dark mark here is feeding, so that's when it ate or drank, I suppose. So you do this religiously for a few days, it calms you down. Are there patterns? I don't know, we did this for quite a while, it's like 3 months or 4 months. So interesting data, but I mean, you don't see anything. The data is weird, it's not digitized. So what you do about it, it's first you put it on top of each other. And of course, the problem is it's somewhat periodic. That's midnight. So it's midnight to midnight. Now you'd really like to see it, you know, appended here so you can see what happens. The interesting things are going on here, of course, right, where the data stops and wraps around. So you take Photoshop, you know, shift it by 1 day and put it side by side, and at least now we can start to see some patterns. At least it sleeps at night more than during the day, which is okay. But so you'd really like to digitize this data, and that's where you need to write code essentially. And this is, for me, that was like one of these border cases. I guess you can try to really detect everything automatically, line by line. You look for dark and light and so on. And you can maybe come up with a robust enough algorithm that does that. I chose to, it's a trade-off. You do this once in your life, so it's not like a tool that you need to use over and over again. So I just wrote a tool that lets me click by hand on each of these gray boxes and records that and puts that in a reasonable format, essentially. So that's kind of, it's always a trade-off between, do you write a really fancy tool and spend a lot of time writing code, or do you just write one that it's just enough to support you as a human in getting the task done? So that's what I did. Data is digitized, then you can write a little application that visualizes it, and now of course it gets much easier to see. At the beginning there was chaos. The sleeping patterns were quite well, actually that's not true. At the beginning it wasn't so bad, and then things after a while deteriorated, became very irregular, and then it kind of stabilized. So that's the sleeping rhythm. We can bring in the feeding points, remove the sleep, and try to see if we can see. I mean, it should somehow stabilize so we can all have dinner together. You know, it's not good if these points are all over the place. And sure enough, you know, if you kind of squint your eyes, things kind of stabilize, and we're all happy family now. Anyway, so that's reason number one. Data is in a weird format. Reason number two is you have some data and you have an idea for a graph, but that type is not available in your favorite tool. What you do, you write some code. So here's an example. That's my resume. It's a typical resume, lots of text, like wall of text kind of a thing. And I often get CVs, you have to parse them in your brain, you have to piece them together. And I thought there must be a better way to do this. How I'd like to visualize my life essentially. And so Excel doesn't really offer much help. It's the recommended charts. Not surprisingly, it doesn't find any recommended charts. So you write some code. You define your data format, the little JSON data format, where you have periods and events, and you can parse that in. And then you write some code. And here's my life in weeks. Every little square is a week in my life. It starts the bottom here where I was born. Blue is education, so elementary school and so on. that's like unknown. No, that was after the school, before the university. I moved off. There should be more of these white spaces in your life, by the way. I realize a lot of things when I look at this. And green is work. So that was my PhD. So now I started work, and I'm always surprised now. I consider myself a seasoned professional now, but I still spend almost the same amount of time in education that I spent actually working, and I'm almost finished. I'm almost done working. So interesting. That was last year. We're about here right now. So don't do this, because 80 is here. There's not that much left. So it tells you a lot of things essentially. But right. Anyway, so my life. So if your graph doesn't exist in Excel or Tableau, basically write some code and do it anyway. That was done with D3 and JavaScript essentially. Okay. Next reason. If you want to add some structure to the data, let me explain you. If you have your standard table with columns, every column is a dimension. Usually you have a number of numeric dimensions, categorical dimensions, and you need to get a feeling of the big structures in that data. You can do the standard things. Parallel coordinates gives you some nice perspective on outliers and groups. You can do scatter plot matrices to look for correlations, but doesn't give you the big picture really. What you'd like to add is some structure that summarizes everything. And there are these algorithms that do that. Multidimensional scaling, principal components, and so on. It's kind of machine learning that goes in that direction. And there are many clustering algorithms and these kind of things that add structure to the data. Problem is you don't really know what they do. You don't have a feeling of what's going on. So if you want to know that, write some code and just make the algorithm visible. You start with a random arrangement of the points. You define some metric between them, similarity metric, and then you just run the simulation. You run the code, the iteration, and structure emerges basically. And that's just one example where, so you can see what's going on now. You understand the algorithm. You see where it may be, where there are problems, and you can do funny things. So here I added an artificial structure to the data, and at the end it spells out 2001 or so, where we used this for our Christmas card in 2001, basically. But it shows the point, you can make algorithms visible, understand what they're doing. This is simple spring-based algorithm. Anyway, and it looks nice. Right. What next? Or something. Right. So machine learning, making that visible. 3D stuff. Sometimes you have 3D. We saw that ring of atoms at the beginning, and the problem with 3D is that if it's static, it's kind of difficult to understand the space, and it's much easier if things move, if you can either manipulate them yourself, but that's not always possible. So what you can do is you can animate it. You can render it in 3D, animate it, and at the same time, as getting a better spatial feeling for this object here, you can also tell a story. You can highlight things as you fly across the surface. You can highlight the things that you consider important. And so storytelling in visualization is kind of a big thing right now. Here it's much more obvious how to do that than how to do it with abstract data. How do you tell a story about the election data or the votes? But there are still some good examples. So again, here you need to write code. I had to write a little flight simulator that lets me define the path and let me turn the camera. Of course, now software exists that does that, but that's expensive and usually doesn't do what you want. So it's kind of cool. So you can highlight these impurities in the surface and things like this. Okay. And the story has an end. Okay, next reason, animations. If you want to drive your animations with data, usually that's also when you need to write some code. Let me give you 2 examples. First, a kind of a funky one. Suppose you have an image of a planet, Earth, and you want to know the distribution of the colors in that image for some reason. How do you go about that? You quantize, you simplify, you quantize both color and space, and then basically you count, right? So counting is not difficult, it's boring, so let's make this a bit more interesting. Let's animate the counting. So that was the first prototype. It counts kind of slow, but you get the point. Basically, you just take each color, all the colored pixels that belong together, and heap them up in a bar chart. The interesting, it's a really simple algorithm. Basically, you just move a pixel on a linear trajectory to where it ends up. And the funny thing is you get this really organic looking movements, but it's just straight lines. If you know, my algorithm just knows the end and it knows the beginning, and it just animates it on a straight line, but still you get this very nice emerging patterns. I love it when you have simple things that have these very nice emerging properties. We made this into our Christmas card for 2016 because it was fun. Now it's faster and quicker and so on. So I could watch this forever. But let's move on. It just keeps going on. So on the animation side, another example now a bit more serious from the hospital here, from the University Hospital in Basel, in the radiology department. They have many people coming through every day, taking X-rays, MRIs, CT scans, whatever. And it's big, it's quite a machine, and the workflow of how these people go through the system, the patients, is computerized. At every point, when you get an appointment, that's recorded. When you show up, it's recorded, and so on, all the way until there is the actual report at the end. And it's important that this is efficient because resources are scarce, people are expensive, and all stages are well documented and understood, but the overall workflow is never really visible. It's very hard to figure out where do we have bottlenecks, and why is it slow in the evening, why is it that. So here's how this looks like. That's the floor plan here in Basel. It's just basically you start by requesting examination, then there is an order entry, person arrives, examination is done, well, they have to change first. Examination is done, then the data goes to the reporting room, then the reporting is done, it's checked again, and finally there's discharge. So that's the workflow, and that's what we would wanted to make visible. And we chose the metaphor of a waterfall. Just basically the different stages go from top to bottom. So that's where you get your appointment, that's where you show up at the counter, that's where you change, and then examination starts, ends, report is generated all the way until it's released at the end. And time goes from left to right, it's the relative time. So, and all the stages have colors. And now we can see someone just basically flowing through this process like this. And I can show this quickly. Let me show this live because this is more fun. So it's a little application that I wrote. We can start play, see what happens. So now it's 1 o'clock at night. There are some emergencies going through, and at 6, 7 o'clock you will see things heat up. People are coming, and there's a lot going on. And after a while, so that's the reports that should be checked. And in the evening, towards 7 or so, we can see all the reports that weren't finished during the day, and it's like a wave. So when I showed this to the people the first time, they were, whoa, that's like a wave that's coming towards us, because you'll see in the morning at 7 they have a lot of work and taking care of all of these reports that they didn't do, and already the next patients are coming. And you can see interesting things, of course. Visualization always shows you data that is not correct. For example, this person here, it's an emergency. You know, they go up the process, which shouldn't be possible. You know, first they get the examination done, and then they go to the changing room. So that's it's upside down, and it's obviously a data problem, because some of these dates are entered manually, so they don't match up. And that's what's so great about visualization. You just see these things. You don't even have to look for them, right? Things like this shouldn't happen. So he gets the report before it was actually done the examination. And then you can see this wave, and it repeats every day. It comes again. Okay, that was the demo. Right, so this provides the big picture, creates the intuition about the relationships. It's not a quantitative analysis, it's a very qualitative, but it gets people thinking. When they saw this, they thought, wouldn't it be cool if there was a real-time monitor that shows us the state of our radiology department at any point in time, that we could have on a screen, and we could see there is a bottleneck, there's going to be a problem, we should have more people. So, because the display here, the one before, is a retrospective view. And so we did some sketches, came up with some ideas, and that's the concept we came up with. So it's still the different stages go from top to bottom, that's time. And we have for each stage now, we have a standardized box, which is twice the expected time. So for each step in this process, usually you have an expectation of how long things should take. So that's in the middle. If it's too long, it's over here. If it's shorter, it's over here. So that's twice. And if it's more than twice, you get into this bin here and just get stuck. It's like way too long. And then you can, at any point in time, this should represent the state of your department. Here's a little example of just a very simple radiology unit. They just have a waiting room and examination place, and you can see now up here it's reverse, because that's the future coming towards the present. So that's the schedule, and they come towards now. Now is here. You can see people who are late, they get pushed out. And so once they get into the process, they jump down, and then it goes this way, waiting room, examination, and so you can basically get an impression. And that was important to them. That's what's done. You know, that's done. We did this. We took data from the big hospital. Let's start it. There it looks much different, just to see how it scales. And so there are a lot of people. We can see again some data problems. So each of these boxes is one machine now. They have five MRI scanners, for example. And there shouldn't be two patients at the same time in the MRI scanner, right? That would be quite tight. It's already tight for one person. But you can see, so there was one person didn't show up, two persons didn't show up. They have a big problem here and here because they are still sleeping down here. And you can see where the bottleneck is, basically. Now, this is sped up by a factor of 10 or so, I think. But we are working now, it's a current project on basically hooking this up to the live systems and providing them with a real-time monitor of the state of the radiology department. And it's done. Okay. Right, so we saw 5 reasons. The last thing I want to show you, there is some time still, right? It's about 5 minutes. Okay, so I'll speed up. Okay. One last project that kind of covers all of the above. That's when it gets interesting. Very quickly, it's now we look at the whole campus, the whole hospital campus. That's the one in Bern, the Inselspital, the University Hospital in Bern, how it looked like in '84. And the story is that as time goes on, the campus changes. Today it looks like this, and the problem is that things are not optimal anymore because they build buildings where there is space and not where it makes sense in medical terms. Also the medical processes changes. So essentially the layout degenerates over time. And right now in all the big hospitals in Switzerland and in Europe, they are tearing down these old buildings from the 70s and replace them. And that's an opportunity to think about how should we arrange the layout of such a campus. And well, let's skip that. So the question is, how do we get from here to these nice layouts that the architects design? They basically tell you where to build, but they don't tell you, obviously, where should your emergency department go, where is the oncology unit. And so in order to figure that out, it really helps if you know what people do in the hospital. Where do they go to? You kind of have some intuition, you know the processes, but do people really follow processes? Here's a counterexample, and that's where the process wants you to go, and that's where people really go, obviously. We're quite inventive. If we just save 2 seconds, that's where we go. So our goal was to find out where do people really move in the hospital and not where they're supposed to be, so that we can base the decisions of how to optimize the layout based on this. And so we collected a lot of data. We didn't track people physically, but a hospital has many information systems where people leave digital traces, and you can collect them and combine them in a big data store and reconstruct basically the path that they took. Now this sounds glorious, but it's a bunch of CSV files. I told you I like CSV files. Anyway, Excel doesn't really work. As you can see, you cannot see much. We have a lot of data, few 100,000 movements. First thing we always do is write some code and look at the data, because people don't know what they want to see. And so here's an animation of a typical day in a hospital. It's night, and then at 7, things start to heat up. White are internal movements, blue are entries, green are exits, yellow are emergencies, so they still happen during the night. Emergencies keep coming. So there's clearly stuff going on, but right, we cannot analyze it like this. So we wrote a visualization application that shows the abstract organizational view. We have all the clinics around the circle. That's the emergency department. Red are people flowing out of the department. So we can see how they have a big connection with radiology down here. The thicker the line, the more patients go back and forth. These are like the freeways. Radiology is central. It distributes people into the whole rest of the hospital. Right. So that's the organizational view. We have the children's clinic over here, which is not connected too much with the rest of the hospital. So there are many things that emerge. When you do this analysis, you can expand clinics to show departments and see point-to-point interactions. So here is where we do, again, these layouts based on, because you know how many patients are exchanged between 2 clinics, you can make a layout that tries to optimize distances, and at least gives you a systemic view of things. And so radiology goes to the center, and the children's clinic goes to the outside. So that's the algorithmic part. We can look at time, of course. Again, that's a graph type that's not usually available, where you flip things around. That's people going out, people coming in. You have lenses that show you the weekly rhythm. You can see Easter holidays and things like this. Of course, you can correlate it with a map, so that you can now see how people have to, that's individual cases where they had surgery, and you can see how they are distributed over the whole campus. Finally, things are 3D in real life. Back to 3D. We can show the path in 3 dimensions. And these are, the interesting thing here is these buildings are not built yet. So what we did is we projected the current paths into new buildings to see how the elevators are going to be used, for example. Right. So they figured out stuff. They did the layout they're currently building, these 2 buildings, not just based on that, but that was an important part. So now that's my conclusion. Almost when people say that, then we're happy. That's, I think, the goal in visualization, is to get this reaction. That's when you know that your visualization was good. Tough, yeah. Anyway, so that's the criteria. That's my conclusion almost. I promised you galaxies at the beginning, so here are some galaxies. So just while we wrap that up, it's an animation through a big scale simulation of cosmological structures where you can see galaxies, clusters of galaxies, the hypergalactic plane that is defined by these clusters of galaxies. Anyway, so here are the galaxies, and that's the end. Yes, thanks for your attention.